This experiment involves the use of sodium borohydride. This chemical slowly decomposes when in contact with moisture in the air. For this reason, the reaction will be conducted using techniques that provide a dry atmosphere. The chemicals will be weighed inside a glove box, which is filled with dry nitrogen gas. Much of modern chemistry is conducted in glove boxes. The main chamber is kept filled with nitrogen gas at all times. It has gloves attached, allowing me to reach my hands into the glove box and weigh out the chemicals. It also has glass windows so I can see what I'm doing. The antechamber allows me to bring supplies and chemicals into the main chamber while still keeping the main chamber dry. There is a door on the front where I put supplies, such as bottles, chemicals, gloves, etc. After closing the door, I flow dry nitrogen gas in and out of the antechamber until it is dry. Then I open a second door that leads into the main chamber and bring in the supplies. Now we are viewing a workstation inside the glove box. I'm laying out some aluminum foil on a tray to catch any messes I make so they can be easily taken out of the glove box when I'm done. Here, I am opening up the door to bring in supplies. I use tongs to grab things that are hard to reach. Then, I close the door to keep the glove box dry. Now I protect the dry box gloves from punctures and dirt by putting on a second pair of gloves. This bottle contains sodium borohydride powder. And this bottle contains ammonium sulfate powder. Now we are weighing an empty glass vial. We do this as a precaution in case we make a weighing mistake with the chemicals later. Notice I need to use tongs to reach the scale. With 2 pairs of gloves, it is awkward and requires a little practice. Now I am zeroing the scale, and I will weigh out the ammonium sulfate before grinding it. As you can see, the weighing process is tedious in the glove box, and so we will speed it up. In this experiment, the powders need to be ground well using a mortar and pestle, otherwise the reaction yield will be low. This is because the crystals of ammonium sulfate are quite large, and they are not very soluble in the solvent we are going to use in the reaction later. So I can't depend on dissolution to break up the crystals and make the molecules available for reaction. Grinding compensates for this by breaking up the crystals as much as possible. The reaction vessel is a very dry glass 100 ml round bottom flask with 3 necks or openings. One neck has a rubber cap for adding the solvent later on. The middle neck is attached to a cylinder of dry nitrogen gas with plastic tubing. The last neck is open to the air. Notice there is also a white magnetic stir bar inside the vessel. To create a dry nitrogen atmosphere inside the vessel, I am flowing nitrogen gas in through the middle neck and out through the open hole for about 5 minutes. I am now going to add the contents of the vial to the reaction vessel. With the nitrogen still flowing through the reaction vessel, I quickly open the vial and pour the powders into the flask. Now I am cleaning the ground glass joint and inserting a cap to seal the vessel. We have zoomed out to show you the bubbler. Nitrogen gas is still flowing through the system to ensure that dryness is maintained. I also place clamps on the glass joints to maintain the seals. So far, I have gone through a lot of trouble to create a dry environment, and I need to do the same for the solvent. Here we have a bottle of very dry tetrahydrofuran, which is also known as THF for short. The bottle is sealed with a bottle cap. The bottle cap has a hole in it that is covered with a rubber membrane. The rubber membrane is pierced or punctured with 2 syringe needles used to deliver dry nitrogen gas in and out of the bottle to keep it dry. Nitrogen gas enters the bottle here and exits here. The exiting gas flows through the bubbler. I will use this syringe and needle to extract 30 mils of the THF from the bottle. Now I will add the dry THF to the reaction vessel. Recall that one of the necks on the reaction flask is sealed with a rubber cap. I will force the needle through the rubber cap and empty the syringe into the vessel. The reaction must be stirred vigorously while heating at 40 degrees Celsius for 1 hour. To accomplish this, the bottom of the reaction vessel is immersed in a preheated water bath at 40 degrees Celsius. During the reaction, we will monitor the temperature with a thermometer. After 1 hour of stirring, the reaction is complete and no longer needs to be protected from moisture in the air. The vessel contains a mixture which can be separated by suction filtration. The ammonia borane is soluble in THF and will be collected in the round-bottom flask at the bottom. Insoluble salts, including some unreacted starting materials, are collected on the filter. We will now remove the solvent from the ammonia borane using a rotary evaporator. Now I am attaching the flask to the rotary evaporator. Once I have the flask rotating, I turn on the vacuum pump, which lowers the atmospheric pressure in the flask. This causes the THF to boil close to room temperature. The pressure gauge confirms the formation of a vacuum in the system. As the THF boils at low pressure, it enters the gas phase and is transported into a cold collection vessel. Here you can see we have lowered the flask into a hot water bath. The combination of heating and vacuum removes the last little bits of THF, leaving only ammonia borane powder in the flask. And now the reaction is finished.